Okay, lesson 5.5, we are going to be graphing logarithmic functions. So we've seen this function notation several times now. It's just now we have a logarithm here because we're graphing log functions, but we've seen it, when we do trig functions, we've had these A, K, D, and C transformations that all were in the trig unit, right? Like where you had y is A, for example, sine, and then you'd be K, x minus D plus C, right? So we've seen all of these transformations before. They are identical to logarithmic functions. So that means the A is going to cause any vertical stretch or compression, right? So the vertical stretch, compression, and the reflection over the x. Your k variable, that's going to be your horizontal stretch compression. And just as there's a reflection over the x when the A is negative, when the k is negative, there is going to be a reflection over the y-axis. Okay. Now, the C value. Actually, you know what? I'm going to do that one in green too because I want to highlight the D value. So C. C is going to be your vertical shift. Up, down. And then D. So let me talk about D for a second. Well, just like every other function, D is going to cause the horizontal shift right. But in the case of logarithms, it is also going to be the location of your vertical asymptote, okay? And the reason for that, let's think back to exponential functions. Well, the actual reason, like the proof, will come in when we talk about properties of logarithmic functions. But in terms of today's lesson, like why is it that that's the vertical asymptote? Like why does the graph have a vertical asymptote there? So that why will be explained by just looking at the exponential function. So take exponentials. In the previous lesson, we did examples where it was like 3x minus 1 or something. That was our exponential function. Well, this minus 1, right, when the C was minus 1, that was the location of your horizontal asymptote. So you would have had a horizontal asymptote right down here, y being -1, and so your graph would have went like that. So if we think about the connection between exponential functions and logarithmic functions, they're inverse functions. So when we were doing that proof in the previous lesson, anything to do with like x on the exponential ended up being a property for y's on the logarithmic, and vice versa. So if you have a horizontal asymptote when at the C value, C being something to do with vertical, so y, well then if we think about connecting that to the inverse, you would expect then on the horizontal, so now you're going to the x, right? So on exponentials, it was the vertical asymptote occurring when on a y transformation. Well, now the asymptote happens on a x transformation because logarithmics and exponentials are inverse functions of each other, okay? So the D value, whatever that number is going to be where you're going to put your vertical asymptote, okay? So if it was like x minus 3, you would have a vertical asymptote at 3. Remember, it's always the opposite, okay? So let's get right into the lesson. we have 4 examples that we're going to go graphing. Any point in the lesson when we're about to graph, try and pause the video and do it for yourself, okay? Because the steps we're going to take to actually create the graph is identical to what we've done in any other unit, right? We're going to be doing the mapping notation. So we're going to be applying the transformations to different coordinates from our parent function and then just mapping them. Okay, so first example, y equals log base 2, x minus 2 plus 3. Well, what transformations do we see here? So when you describe transformations, remember you're always reading them left to right. So the first one I see is I'm going to talk about this negative 2. And just so I don't have to like write out like, you know, this vertical stretch compression over and over again, just for the sake of making this video shorter, I'm just going to say it's going right 2, okay? But on a test, please write out the full sentence. Like you would say horizontal shift left 2 units or right 2 units. Okay, so we talked about that one. The next one we talk about is this plus 3 here. So that plus 3 is going to be up 3. Now, to create the mapping notation, we need a set of x and y points that we apply our transformations to. So the transformations that we're going to apply, all right, the x's are going to be shifted right 2 units, that's why you're adding 2, and your y's are going to be shifted up 3, that's why you're adding 3. But we need a set of points. We need a set of coordinates that are coming from the parent, okay? And this stumps a few students, okay? Because what coordinates do we use? Like, what are the obvious ones? Like, when we think back to quadratics, right? Like, you would have chose values. You would have chose, like, 0 on the x, and then you would have chose 1, 2, and then you did -1, -2. And the reason you chose these points is because when you chose those x coordinates of -2, -1, 0, 1, and 2, it made it really easy to just get points on the y when you squared them. So this is like y squared, right? So when we're doing logarithms, it's the same thing. But you're always asking yourself, okay, so my parent function, log base 2 of x to the y. So what coordinate do I plug in here, right? Whatever goes in there, that's the x coordinate, right? Like that's you're asking me an x value. So what numbers are easy? Let's get 3 of them, okay? What 3 numbers make it easy to calculate a logarithm? Well, it ends up being the base of the logarithm. So 2. 2 is a really easy number because what you're asking yourself is you're saying 2, if you think about how to write a logarithm, you're asking yourself 2 to the y equaling x. So you are choosing these values of x right here. So if I choose a number like 2, okay? So like let's say I chose the number 2 for my x. Well, what do I put 2 to the power of to get this number that I chose right here? Well, you would choose 1. Like 2 to the power of 1 gives you 2. So 1 on the y. Another easy number would just be choosing what 2 to the power of what gives you a value of 1. So I'm going to choose the x coordinate 1 in this case, right? Like I'm choosing x coordinate of 1. So you have to think about what y gives you 1. Well, 2 to the 0. So at an x coordinate of 0, you're at 0, right? Like what you have just said here, like let's just take this example right here, like this coordinate what I've done here and think about it in logarithmic form. What you were saying is that when you go log base 2 and the coordinate I've chose is 1, so that's why I'm plugging in for the x, I'm plugging in 1 right here. Log base 2 of 1, what do I get? you get 0, right? Your y is 0. So that's what you're doing. That's like, it's tough because in order to get these points, you have to always be thinking like exponentials, okay? So then the last point, what's another easy point to get? Well, think about the reciprocal of this base. 2 to the what gives you x, okay? Well, I'm telling you, take the reciprocal of whatever this base is. That's going to be the next easy point. So the reciprocal is 1/2. So what y coordinate, if I chose this to be 1/2 right here, my x, what y would give me that? Well, -1. So those are generally going to be the points that you want to use, right? The point you're going to want to use are going to be like your base, whatever the base of the exponent is. You're going to want to use 1, and you're going to want to use 1 over your base, okay? And we'll see that throughout the other examples too. Sorry, there's something stuck in my throat. Okay, hopefully better. Let's keep going. So we're just transforming these points, all right? So I'll do the first one, I'll write it out, but like for the rest of the video, just know that this is what I am doing when I'm transforming them, okay? I am taking this 2 right here, that 2, subbing it in for that x right there. So 2 plus 2, and then this y right here for this y right here. So then that would be 1 plus 3. So 2 plus 2, well, that is 4. And then 1 plus 3, well, that is 4 as well. So this coordinate of 2, 1 gets transformed into 4, 4. Okay? So your next one, when you substitute 1 in, you're going to get 3. When you substitute 0 in, you get 3 as well. When you substitute half into the problem, you're going to get 2.5. Work in decimals, all right, just because you're going to be plotting that point, so decimals make sense. And then when you substitute -1 in for the y, you're going to get 2. So let's graph those points, okay? But just like exponential, it helps if you start by graphing the asymptote. So as I said, the asymptote is going to be at whatever the value of d is. So in this case, d is going to be 2. So you're going to be putting in 2 here. There's your asymptote. And then that kind of gives us a ballpark of where to put your other coordinates. So on the x, we're going to need the coordinate 2.5. Don't want to circle it. 2.5. We'll also need 3, and we'll need 4 on the x. On the y, we're going to need 4. We're going to need 3 as well, and 2. Okay. So the first point we calculated was 4, 4. The second one was 3, 3. And then the third one is 2.52. So we can kind of get an idea of the direction we're going, and then we hug the asymptote. Okay. And let's call this f of x, just so we can give our graph a label, right? And so instead of it being y, f of x. So f of x. And there you go. Okay. So let's state the characteristics. The domain, well, because we have a vertical asymptote, that means we're going to have a restriction on our domain. In terms of this, all the x values need to be bigger because we are on the right side of it. We are on the right side of the asymptote. The range, well, the characteristic of a logarithmic function is that you don't have any restriction on the range. Your asymptote, well, we've already said it's at x equals 2. We can see that our function is increasing because when I look left, when I read from the left to the right, I can see that my function is going up, okay? And that's essentially what this is saying here too. This is end behavior. And it's saying that as x goes towards positive infinity, well, because we're going up forever, we're increasing, we are also going towards positive infinity. Okay, let's do another example. And again, pause, try it for yourself, all right? So we are given the function y equals negative 2 log 3x minus 5. So what transformations are we looking at here? Well, we're going to again read left to right. So the first thing I'm going to talk about is that negative that's on that 2. That's going to be a reflection over x. The 2 is going to be a vertical stretch by factor 2. And then the negative 5 on the back on the end there is going to be down 5 units. Okay, I'll say it again, like please use the correct terminology on a unit test, but just for make this video go faster, I'm gonna say it like that. Let's get our mapping. So once again, we need x and y's coming from our parent function, and we are going to transform those points by applying, well, nothing to the x, because here we have no k and we have no d value. So you just write your x coordinates, nothing happens there. The y coordinates are going to be multiplied by negative 2 and then being minus 5. So we need our parent coordinates. So again, pause, try for yourself, figure out which ones I'm going to use. So I look, what is my parent function? In this case, it's log 3x. So the points I'm going to be using is the base. So I'm going to choose 3 for my x. So 3 to the what, right? Like if I plug in 3 for this x right here, what do I get? So what you have to be thinking about is 3 to the what? 3 to the what gives me 3? Well, 1. Okay, my next x coordinate that I told you to use was 1. So I'm asking you, okay, well, log base 3 of 1, what do you get? 0. It doesn't matter. It doesn't matter what base it is. Log of 1 is always going to be 0. And then the other one I told you to use was a reciprocal of the base, so 1/3 in this case. And that would end up, if you did the same process, you would get negative 1. So let's transform those points. So I've already said that we are not going to have any transformations on our x, so that's still going to be 3. That negative 1 is going to result in that being that positive 1 is going to result in being negative 7. If I substitute in 1 for the x and 0 for the y, I get minus 5. And then if I put in 1/3, I still get 1/3. And then negative 1, I get negative 3. Perfect. So let's sketch our graph. Let's start by putting our asymptote. So as I said before, the d here is 0. So that means you still just have an asymptote right here at 0 at x of 0 is your vertical asymptote. Then let's put our x coordinates that we're going to need on our graph. So I will need the coordinates not minus, 1/3. I will need 1 and I will need 3 on my x. On the y, I'm going to need negative 3, negative 5, and negative 7. So when I plot my coordinates, I'm at 3 and negative 7, so that's right here. I'm at 1 and negative 5, and 1/3 and 3. So my curve is looking like this. There we go. And same thing, let's just give this a title, f of x. That way we can call this f of x without writing the whole equation out. Okay, so we have our graph. Now let's state our characteristics by just looking at the graph. We can see that we have a restriction on our x, and the x's are on the right-hand side of the asymptote, or sorry, your curve is on the right-hand side of the asymptote. That means your x have to be bigger than whatever that asymptote is. Your range is y belongs to real numbers. The asymptote, as we've said, is x is 0. This function is increasing or decreasing? Well, if I read left to right, I can see that I am going down forever. So this function is decreasing. And because it's decreasing, that means y's are going to negative infinity as you go to the right. Second example, let's state our transformations. So y is equal to 5 log 4 1/3 x plus 1. So if I talk about things left to right, I'm going to first talk about that 5 that I see here. So that 5 is going to cause a vertical stretch by a factor of 5. The next one that I'm going to encounter is this 1/3 right here. So because k is a third, that means this whole function is occurring at a third of the speed, meaning that it takes 3 times longer for things to happen. That's why it's stretching itself out. So this is a horizontal stretch. Okay, and then same thing, factor of, remember it's always 1 over k. Okay, so in this case, if it's 1 over 1/3, that's 3. So by a factor of 3. Then the next one you talk about is that 1 that's on the inside of the bracket there. So that would be a left 1 unit. Okay, now let's do our mapping. So let's get x and y coordinates from our parent function, and then we will apply our transformations. So the x's are going to be multiplied by 3 because we're stretching them by a factor of 3. And then we're going to shift them left. So we're going to subtract 1. And then your y's just get multiplied by 5. Okay. So let's get our points from our parent function. So what coordinates are we going to use? Well, our parent function is the function y is log 4x. So that means I'm going to want to use my first coordinate being whatever the base of my function is. So 4. And if I use that coordinate, 4 to the what will give me 4? Well, 1. Okay, the next coordinate I'm going to use is 1. And then log of anything, log 1 of an event, like whatever base, is always going to give you 0. And then the next third coordinate you use, this one right here, is 1 over b. So in that case, we're going to be using 1/4. And then that will give us a y coordinate of -1. Okay? So we're just getting nice, easy points to work with. Let's transform them. So when I transform the 4 and the 1, I'm going to get 11 for my x, 5 for my y. When I plug in 1, I'm going to get 2 and 0. And then when I plug in 1/4 for that x, that's 3 times 1/4, subtract 1. So that's essentially like me saying 3/4 take away 1. So you're going to get -1/4. And then if I plug in -1 in for the 5, I will get -5. Okay, let's graph our function. So we start by putting our asymptote. We are shifting the whole curve over left 1 unit, right? So if you think, your base function is usually having an asymptote at 0, right? The one that has no transformations. So your asymptote will move left. And that makes sense, right? Like right here, like the d is -1. So you are going left. The whole curve, right? Everything to do with the curve. The asymptote is part of the curve. Everything moves left. So that's why you have an asymptote by -1. Let's put the other points we need on the graph. So the ones we're going to need to have are -1/4, 2, and 11. So let's say that that is -1/4. Let's say that this right here is 2. And let's say all the way over here, this is 11. Then we'll need 5 on the y, We'll need 0, so right at the origin, and then we'll need -5 right down here. Now plot the points. So 11 and 5 was your first point. 2 and 0. And -1/4 and -5. Let's see if I can connect my dots. Not bad. Okay, and that's f of x. So that is everything I'm looking for on a test, by the way. Like you can see, I'm asking for you the title, I'm asking for you to label the asymptote, and then show me the 3 points, okay? And then that you get full marks for graphing it. Okay, domain, well, we're on the right side of our asymptote, so x belongs to real numbers, and the x's need to be bigger than your asymptote. Oh, sorry, -1. Your range, well, y belongs to real numbers. Your asymptote is at -1. It's a vertical asymptote. And let's specify that. I should have actually specified on the previous ones, but that's okay. And then this function is increasing, so that means your y's are going towards positive infinity. Last problem, and probably the hardest one for last, okay? A couple things that have changed here in comparison to the previous ones. Well, first one being that I have a half as my logarithm. And then there's something that I have to do here first, and let's see if you can catch it, okay? So if you need to, just pause and then see if you can figure out what it is. Whenever you see a number next to the x, right, like this, and there is no bracket, okay, because look, there needs to be a bracket. There needs to be a bracket here separating the number and the x. So because I don't see that, that tells me I have to first factor that -2 out. So rewriting that function, that would be y is 3 log 1/2. I will factor out the -2, and that leaves me x, and then that -4 being divided by -2 plus 2. So if you didn't factor it out, what you would have told me is that, hey, I see a -4 here, that tells me that that needs to have an asymptote at -4. But that's not the case. We can see right here that there actually is an asymptote at -2, okay? So you would have got the wrong asymptote. Your curve would have looked wrong. So make sure you're always on the lookout, ready to factor. So that is the curve that we're using, and let's state our transformations based off what I see there. So that means we're going to have a vertical stretch by a factor of 3. The next thing I'm going to encounter is the negative here attached to that 2. So that -k tells me I'm going to have a reflection over the y. Then the 2 says everything happens twice as fast, so that means there's going to be a horizontal compression. Everything's coming together. Factor of, and again, 1 over the value, so that would be 1 over 2 in this case. And notice I'm not saying -1/2, okay? You've already talked about the fact that that 2 is negative right there. So you're really only concerned about what is the actual factor, like what's the numerical value that you're compressing it by. And then lastly, talk about that +2 inside the bracket. So that's going to be a shift, and it's +2, so left 2 units. Okay, let's get our mapping. So we need x and y coordinates from the parent, and then we are going to transform those parent points by first taking our x coordinates and multiplying them by, well, they need to be compressed by a factor of 1/2, but they also need to be reflected, so you're multiplying by -1/2 here. X, and then you're shifting them left, so that means you put a -2 here. Okay, your y coordinates are going to be 3y, and then there is no vertical shift. Let's get our parent points. So think this is the parent function right here. So log 1/2 x. Well, just because there's a half there, the rule, like the same thing applies. You're going to put the base, right? So you're going to, for your first x coordinate you're going to choose is the base of your logarithm. So that means, like, essentially what I'm saying is evaluate this log base 1/2 at the value of half. That's what I'm asking you to do. So then half to the what? Half to the what gives you 1/2. Well, just because it's a fraction, it's the exact same thing as everything we did up here, right? When you have the base and the thing that's on the inside of the argument being the same number, it will always result in it just being 1, okay? So your first coordinate is always going to be the base and a y value of 1. Okay? Well, the next one I told you to use is 1. Well, taking the logarithmic of 1 will always result in 0. And then you do the reciprocal of the base. So the base being 1/2, well, in that case, the reciprocal is now 2. So taking log base 1/2 of 2, right? Well, 1/2 to the what gives you 2. Same thing. -1, just as you did before, okay? So don't get afraid by a fractional base in a logarithm. It's the same thing as all the other numbers. Well, now we're going to work with our fractions a bit, okay? So what happens when you have a half and you're plugging it in for the x right here, and then you're subtracting 2? Well, just use your calculator, honestly. And you're going to get -2.25. And then plugging in 1 for the y there, you'll be at 3. Your next coordinate, well, when I plug in 1, I'm going to be at -2.5 and 0. And then lastly, when I plug in 2 into the problem, I'm going to be at -3. And when I plug in -1 for the y, I'll be also at -3. Okay. Start by graphing your vertical asymptote. So the vertical asymptote is occurring at -2 because I see a +2 in the brackets. So x of -2. And then let's put our x coordinates down. We need a coordinate at -2.25. So that's actually a little more negative. So now we're on the left side of the curve. So -2.25. And then this one would be -2.5. And then -3 was our last coordinate that we needed on the x. We need a y of -3, 0, and 3. So let's now plot our points. So at -2.25, that's when we're up here at 3. At 2.5, you're at 0, so right down here. And then at -3, -3. Right there. So your curve looks like this. Okay. So that is f of x. So now just reading off the characteristics right from the graph, if we look and state our domain, it's x belongs to real numbers, but because we're on the left side of the asymptote now, that means you're going to be x values less than the asymptote, okay? So careful with that one. Your range is y belongs to real numbers. Nothing changes. Your asymptote is, it's a vertical asymptote at x of -2. If we read the graph left to right, so if I go this direction, I am an increasing function because my y values are getting bigger. And then this last one here, again, careful. It's asking you what's happening on the left end of the graph, okay? Because we're on the left side of the asymptote now. It's saying what happens as you go this direction. This is what happens when it says x going to -infinity. Well, we see that we are going down forever. So y is going towards negative infinity. All right, and that is the lesson. I'll see you in class.